Nigella told you, I am actually a paleoclimatologist. But I'm actually going to be talking about some of the risks associated with future climate change, global warming, and the possibilities for abrupt climate change, and what the past record of climate might say about that. Now, actually, traditionally, I've had a bit of trouble explaining what it is that a paleoclimatologist actually does. Mostly that's to my parents and other relatives. And in fact, a few months ago, I thought I was in great luck because this blockbuster movie came out where paleoclimatologists actually played a leading role in the film. Dennis Quaid, in fact, played a paleoclimatologist. So I thought that maybe from the time that the movie came out that I could just say, oh, well, you know that Dennis Quaid character? That's me. Anyway, well, it turns out the movie wasn't quite the critical and popular smash hit that they are anticipating. And in fact, frankly, I think though Dennis Quaid is a great actor, maybe the discipline of paleoclimatology might have been a little bit better represented by Brad Pitt, George Clooney type, or maybe a Vin Diesel type, alternatively. Anyway, despite the actual schlock and the stretching of one's credulity that went on with this movie, the actual theme was actually quite important and went right to the heart of assessing the risks of future climate change. Namely, it was asking the question, will the actual variability of climate increase as a consequence of global warming, as the average temperature of the planet increases? So I think you're all familiar with at least the concept of global warming, the fact that as we increase the burden of carbon dioxide in the atmosphere through the burning of fossil fuels, the temperature of the surface of the Earth on average will inevitably rise. And in fact, I think most people agree, 99% of us in the business agree that the 20th century already has experienced something of the global warming in that the average temperature has increased to the tune of about 1 degree Celsius, or roughly almost 2 degrees Fahrenheit worldwide. And if you project that into the future, it is inevitable that the burning of fossil fuels will further increase the burden of carbon dioxide in the atmosphere. And in fact, if you project the best predictions for how the average temperature of the planet will change over the next century or so, there's almost consensus in the form of this report put out by the so-called Intergovernmental Panel for Climate Change, IPCC, that the temperature will rise anywhere from 2 to 4 degrees Celsius on average. But what does that really mean? Average temperature is kind of an abstract concept in a way that people really can't grasp. After all, what we really care about is how things are going to change where we are, or where the crops are. And in fact, if you ask most economists or sociologists, what's really most important about assessing the risks of global warming is whether the changes would occur too abruptly for society to handle, or whether the extremes of climate would be exacerbated in a way that would be difficult for us to deal with. And so probably one of the most important questions to ask about the global warming scenario is whether the variability of climate will increase. And in fact, there's very little consensus on this, this question at all. Now, there's a variety of ways that you could go about trying to address this question. One is to try and charge computer models with trying to show how the year-to-year extremes of climate might change in an overall warmer Earth. So that's certainly one approach that's being employed here and other places. Another approach is to make repeated observations of the climate system in hot spots of or regions that we think are important, and then gradually over a number of years build up a sequence of observations that would allow us to have some better sense for the future evolution. So that's another approach which also is being employed here and elsewhere. But what I do is actually try and work backwards, try to develop as comprehensive a historical perspective on climate variability as possible. First of all, that allows us to be able to discriminate between what is natural variability versus what might be, for example, forced by man's activities. But it also allows us to have some better gauge on the overall mechanisms of climate change and see how those mechanisms of climate change might operate over fundamentally different average climate conditions on the Earth. Typical example is how things behaved during the last ice age, when we know things were globally up to 5 degrees cooler than they are today. So that's my approach, and what I'm going to do is try to walk you through a couple of examples of my own current activities in trying to reconstruct the range of natural variability in the main sources of climate change that we know about today. What I'm going to start with is a discussion of the El Nino phenomenon, which certainly is responsible for the bulk of the variability in climate on a year-to-year basis in our current climate conditions. And then if I have time, I hope I will have time, I'll run through another source of climate variability operating on longer time scales, but still time scales that are relevant to the human condition. And actually, what I'm talking about here is the fact that the ocean's overturning circulation delivers heat to different parts of the planet, and in so doing affects the climate. And so if you interrupt that process of the ocean's overturning circulation, you could cause cataclysmic climate change in some regions. And this is actually the subject of the Schlocky movie. But what I want to start with is the El Nino phenomenon, because that's probably something that's more intuitive to all of you, mostly because you've actually lived through several El Nino events. And as I said, it is responsible for the bulk of the climate variability that we know about today. So in order to think about how global warming might affect the El Nino phenomenon, we have to actually be able to characterize its operation today and as thoroughly in the past as possible. Now, just to remind you what El Nino is, I think you all have a pretty good feeling for it. In fact, if you look on any climate website out there on the web, you'll see a cartoon like this one describing the change in the characteristics of the Pacific Ocean from so-called normal state, where warm water is piled up in the western tropical Pacific, and there's a very thick wedge of warm water as the trade winds are blowing from east to west, piling warm water there. And because there's very intense heating at the surface, then you also have rising motion in the atmosphere, so-called convection, atmospheric convection, and as a consequence, very heavy rainfall. Now, during El Nino conditions, what happens is that sort of very asymmetric wedge of warm water sort of more or less shifts eastward, and the pattern of temperature is much more uniform across the Pacific Basin as a whole. Because the location of warm water has moved eastward, now so does the region of where rising motion in the atmosphere occurs, and as a result, zone of intense rainfall tends to shift eastward along with the warm water. Now, basically, as far as we know, as far as any evidence will tell us, the Pacific has been cycling between these two states every few years or so for at least the last million years of observations. Now, of course, given the fact that this large wedge of very warm water in the Pacific represents probably the single largest heat engine on the planet, if you perturb it, you have the potential to disturb climate worldwide. And in fact, if you look at the impact of El Nino events globally, this is just giving you one picture of the changes in rainfall associated with El Nino events and the potential economic impacts. So as I mentioned, the Central and Eastern Pacific experiences enhanced rainfall. Australia, Indonesia, and South Asia all experience relative drought, some cases very seriously. In our area, the impact of El Nino, as you probably all are aware, include enhanced rainfall and greater probability of storm surges. But nevertheless, the point is that if this system were to be perturbed in a way to make these cycles, despite the fact that we've lived through many of them, if the cycles were to become more intense somehow, say the drought would become intensified, or the flooding in the areas that experience flooding would be intensified, or if the persistence and frequency were to change in a way that would kind of mess up our expectations. For example, if we were locked into a state of permanent El Nino, for example, or if El Ninos didn't come for many years when we were expecting them to come, providing, in our case, the enhanced rainfall, then there would be very serious economic repercussions. So we have to be able to actually think about the question of what might happen to this system in an overall warmer world. And in fact, many people have made the argument that El Nino has been becoming more intense and more frequent as the Earth has warmed up over the course of the 20th century. Not the least of which because the very last El Nino event was the strongest event of the 20th century. So people have looked at this event, and what you're viewing here are the departures from normal temperatures. So in the red you see areas of enhanced temperature, and in the blues you see regions where the ocean has cooled. But people have looked at this and said, aha, we're warming the Earth, and look at El Nino is becoming more intense. In order to be able to have any confidence that that's a relevant claim, you have to be able to characterize the full range of natural variability of the system. And so what I'm trying to do is actually provide a very long history of the El Nino phenomenon using geological materials. Now, this picture was put together using data from satellites, so you can determine the temperature of the skin of the ocean by sensing the electromagnetic radiation that's coming from the Earth's surface. And so you can get a very comprehensive map of temperature information for events like this. And even, I just downloaded this today. This is our current this current state of the Pacific for anybody who's interested. And basically not much is happening that's unusual or departure from normal or average conditions for this time period. On this basis, you know, the internet age, you can, with 3 or 4 clicks, develop a very a detailed sense of what's happening to the ocean. And actually, for anyone who's interested, this condition will probably lead to near neutral El Nino conditions in the December through February season. And so we're not expecting anything extreme happening this year. How would you actually go about reconstructing this phenomenon in the past? We don't have access to satellites. Satellites only came online since the early 1980s. Humans have actually only been taking measurements of the temperature for the last 120 years or so, 150 years maybe now. So we have to actually resort to other means aside from human or instrumental observations of climate in order to make reconstructions. And that's where our friend Mr. Coral comes into play. So what I do is actually try to make quantitative estimates of the temperature of seawater by looking at the chemistry of coral skeletons. And so what we do is actually sample both living and fossil coral colonies for their record of climate. Most people think of corals as something they might see on or have on their tank of their toilet, the kind of feathery finger coral type things. But what we actually look for are the massive head corals, such as depicted in the top photograph, that actually cement in the form of calcium carbonate, chalk. This is a big hunk of chalk. They cement in and capture a record of the ambient seawater. These big, large head corals can attain ages of 300 or 400 years. Sometimes this fellow that you see here is probably on the order of about 30 years or so, something like that. Typically, corals add new skeleton at about 1 centimeter for every year. That's the rate at which they accrete, and so you can just make that conversion. This guy is probably about 35 or 40 years. This represents about 35 or 40 years of growth. So not only do we sample the living ones, and by the way, the sampling process doesn't harm the corals. We cap over the hole that we create, and just like coring a tree, the colony reestablishes itself so we can safely do this without harming the coral. But we also sample corals that happen to be thrown up on the beach, perhaps by large storms, and therefore extend the record beyond the range of living corals. what kind of climate information do we get out of this big hunk of chalk? Well, essentially what we do is look at the chemistry of the coral skeleton. And down below here is an X-ray of a slab of a coral core. Once we take a core, we make a slab and then work on the slab itself. And what you're looking at down below is an X-ray. Corals do add annual bands like tree rings, as Nigella mentioned. In some cases, the width of the rings varies with climate, just as tree rings do. But in our case, we're trying to get a much more precise view of the physical characteristics of the surrounding seawater than the actual width of the rings would actually tell us. So we rely on chemical means, and we needn't bother to go into what those means are. I will just tell you, for anybody who's interested, specifically what's being shown here is the relative amount of heavy oxygen relative to normal oxygen. Normal oxygen has 8 protons and 8 neutrons, but oxygen can also exist with 8 protons and 10 neutrons, giving it a mass of 18 instead of 16. And so the incorporation of oxygen, heavy oxygen, into the coral skeleton actually turns out to be almost strictly, in some locations, a function of the temperature of the surrounding seawater. So here in this picture you can clearly see that the variations in the amount of heavy oxygen is following almost indistinguishably the temperature that you could measure or actually download measured by satellite. And so the upshot is that we have confidence that these coral skeletons are operating very nearly like meteorological buoys, in a sense, only they've been there for millions of years, and they're just waiting to be tapped. It turns out that over the years, the last decade or so, my group as well as others have tapped living coral records at various locations, and so we can begin to fill out the map. But you can see that the number of coral islands that where these records have been produced is somewhat limited. So probably a greater utility of these coral records is that they will allow us to go extend well back into time, well before man was taking observations. But we can at least, using this network of corals, as well as the available instrumental record, say something about fairly concrete about the changes in the El Nino system over the 20th century. So what you're looking at here is the swings in temperature in the equatorial Pacific, the central equatorial Pacific, associated with El Nino and La Nina events covering the 20th century. Excursions in the up direction indicate El Nino events where temperatures in the central Pacific rise in excess of 2 degrees Celsius. Anything in downward direction indicates a cooling or a La Nina event. Just to give you some perspective, the last event there is the 1997-98 event. And you also see the 1982-83 event featuring prominently in the instrumental record in black. Both of those events you probably are imprinted on your memories here as having a strong influence on La Jolla's climate. Down below is just a smooth version of what's on top, just to highlight the swings from El Nino to La Nina events. And so on the basis of this evidence, people have actually made the claim that the late 20th century El Ninos were more intense and more frequent than anything that came before, and therefore so the claim goes, we've already influenced the El Nino system with the global warming. Well, just by eye, it's a little bit hard to substantiate that claim. After all, things are wiggling up and down all throughout the 20th century. If you do a bit more subtle statistical analysis, what you find is that the period from the 20s to the 60s basically was one of relatively reduced variability in the El Nino system. The El Ninos that did come tended to be much slightly less intense, and they came less often than those before or after. So essentially this is what we know from the instrumental period, and it's almost anybody's, that people could make any claim that they wanted to essentially about how unusual the late 20th century was. What we wanted to do was go back, as I mentioned, much further in time, and in order to do that, we actually made use of these fossil corals that were distributed on the beach in this island in the Central Pacific that's very close to the heart of the anomaly, where that's very close to the center of action where things are changing most during an El Nino event. And what we did was to drill into these very skeletons. Actually, this was the dissertation project of a student of mine who finished up a couple of years ago, Kim Cobb. So when we say we, it's the royal we. It's actually mostly her work, and her blood, sweat, and tears went into this. But on the other hand, she did actually get to visit places like this for her field work. Now, looking at this assemblage of heads, you don't necessarily know how old anything is, so a priori we didn't know what to expect from this collection. But it turns out things are, the analytical procedures are good enough now that we can take a sample of these coral, fossil coral heads, and even if they are 1,000, 1,500 years old, we can date them precisely enough to maybe even a precision of plus or minus 2 years. So we can say with that degree of certainty these days just how old these things are that are lying on the beach. So we can characterize the collection of corals that was sampled on this island in the Central Pacific in this way, and to our great good luck, what we found was that there was a very nearly continuous distribution of coral heads covering the last 1,100 years or so, even though each individual head was anywhere between 50 to 100 years long. When you string them together, splice them together, we might be able to create a very continuous picture of El Nino or climate variability in this very important location. Just to clue you into the color coding here, the blue bars are the heads or samples that we've actually already analyzed. So you can see it's only a very small subset of the entire collection. The yellow is what's actually running in the lab right now. I could have actually filled in a bit if I had been industrious with making plots, but the important thing is that there is the potential to create a continuous record of climate variability at a sampling interval that is as little as 1 month. So eventually we'll have a picture of tropical climate variability extending 1,100, 1,200 years, every single month going back. That's our goal. What does that, the picture that we have so far look like? Well, again, using this, this substitute measure for temperature, the relative amount of heavy oxygen in the coral skeleton, which you can actually scale to temperature fairly precisely in this location given by that blue bar there. So that gives you a sense of scale. What you're looking at here is the sort of windows of variability over the last millennium. You can see that the late 20th century is certainly the warmest that this location has experienced over the last 1,100 years. So what that means is, in a way, that's good. It means that we can actually compare the conditions of the late 20th century with conditions that were quite different in the early part of the last millennium. So this is just the raw data, if you like, comprising, in this case, about 16 or 17,000 measurements on our instrument down in the lab. So it really was a lot of work on Kim Cobb's part to put this together. No small achievement. But just to cut to the quick, we can actually look at the variability of El Nino in those coral sequences, and now I've sort of collapsed everything together just so it fits on the same page, taken all the gaps out. You notice the year scale up above, there are gaps between that. Eventually we want to fill in those gaps, but for the time being we can at least look at these fairly substantial windows and see how El Nino evolved or not over the course of the last millennium. And what's pretty obvious just by looking at this compilation here is that basically there's no pattern at all. If you want to make, you'd be pretty hard pressed to make the case that the late 20th century was at all unusual with respect to the severity or frequency of recurrence of El Nino when you compare it to times past. And in fact, you know, we think of the 1997-1998 event as the largest ever. Well, not according to the corals. The largest ever, at least that we've sampled, occurred during the 17th century, during the height of the so-called Little Ice Age in Europe. Over a 30 to 50 year time period, certainly the energy and variability in the El Nino system in the 17th century exceeded anything witnessed in the 20th century. So that's interesting right away. Second of all, what you can get a sense from this picture is that there are times when the El Nino system was relatively quiescent for very extended periods, 20 to 30 years, and then all of a sudden, boom, giving rise to fairly intervals of fairly intense El Ninos. So what that says is that the system has the capacity to change very abruptly from one characteristic to another. This is sort of very common of chaotic systems, so where internal interactions govern the behavior. So the upshot here, just to summarize, is that if we ask the question what the natural range of tropical climate variability recorded in our corals, we'd have to say that the natural variability that we see exceeds anything that was experienced in the 20th century. Furthermore, as far as we know, as I mentioned before, El Nino has been going on at least the last 200,000 years, if not longer. Now we can also say that there's really no consistent relationship between the state of El Nino, the characteristics of El Nino, and the global average climate. So in other words, the most intense, well, for example, the most intense El Ninos occurred when it was relatively cold, not when it was relatively warm. Essentially, we've actually found no relationship between the average climate state and the characteristics of El Nino. Having said that, somebody could take me to task and argue, well, yeah, but the changes in global climate state over the last 1,000 years were relatively subtle, and so it still might be the case that El Nino could change when climate conditions are very different than they are today. One example might be the ice ages, but another example might be if global warming reaches a very large extreme. Now, also, one last point that's very important is that we see evidence for regime-like behavior. It means that things can change suddenly, presumably on its own, without any kind of forcing or monkeying from man's activities. So we can then go on to ask what the implications are for future, a lot of these are sort of downers in a way. One implication is that we certainly can't make the case that, very strongly at any rate, that we have already affected the El Nino system with our activities. That certainly just won't wash if you view it in the context of the geological evidence. What is also the case is that we have to be prepared for sudden changes in the system. We've seen very clearly that there can be extended intervals where we don't have an El Nino occurring at all, and then that goes suddenly to the opposite extreme. So regardless of what we think about global warming, it would be foolish to ignore that kind of evidence. And so when we think about building policies for water use, energy use, for example, we have to factor in the fact that the climate system can change without warning, apparently. Now, unfortunately, too, what it means is that if we want to build a long-term projection or evolution of the El Nino system, or even maybe build a probabilistic model for how the system works, our evidence suggests that that would be a difficult task and sort of a bleak prospect, simply because the system is chaotic. Okay, so let's see. It looks like I have just about expended all my time on the first part, which actually is not uncommon. I tend to gab quite a bit. I had hoped to actually get to this other source of climate variability, dealing with the ocean's overturning circulation. In the interest of time, I can just maybe briefly describe what we're doing rather than go through the setup. It essentially asks the question of whether this kind of circulation that delivers heat from the low latitudes to the high latitudes could be interrupted, destabilized. And if it were the case that this kind of overturning circulation would be destabilized, then you could imagine some parts of the world that are the beneficiaries of that heat redistribution, say, for example, Europe, Great Britain. The climate in those regions could vary substantially. Why do we think that might be the case? Well, because there are examples from geological archives like ice cores, in this case the Greenland ice core, covering the last 100,000 years or so of Earth history. And if you drill in, the Greenland ice cap is 3 kilometers thick roughly. If you drill into it, the first half of that ice cap, you look at the chemistry of that ice that should be sensitive to temperature. Basically, no great shakes. Not much is happening at all. Let me see if I can use a pointer. Right. So the last 10,000 years of Earth history, apparently very quiescent. But all of a sudden, when you get into ice that was deposited 20,000 to 80,000 years ago, when the Earth was in the midst of an ice age, essentially all hell broke loose with respect to the climate system, at least locally here. In fact, this is the whole record of this chemistry of the ice, again measuring the relative concentration of heavy oxygen in the frozen H2O. Down below, several events numbered above here are stacked on top of each other to give you a sense of the behavior. Basically, very abrupt warming to the tune of maybe 10 to 12 degrees Celsius. That quantification of that temperature change goes on in laboratory of Jeff Severinghaus down here at Scripps. So this is what he works with primarily, but another important characteristic here is that the change happens on timescales of 3 to 20 years, so certainly within our lifetimes. Suffice it to say that if a change of this magnitude occurred again in the future, it would have very severe repercussions for society. So we have to actually think about whether these changes are at all relevant to the future climate in a warmer Earth. Now, most people think that most people think that the ocean's overturning circulation was involved with producing that characteristic variability observed in the ice core. And so how would you actually sample and get at and test what exactly was happening in the ocean during those times of cataclysmic change recorded in the ice core? Well, here, unlike in the case of the corals, where corals add a centimeter or so every year, the oceans, the seafloor, add a centimeter of sediment every 1,000 years, roughly, on just as an order of magnitude. So essentially, what we do is send some kind of coring device down into the seafloor. In cases of just ramming a piston home, we typically get anywhere from 10 to 20 meters, and that gives us anywhere from 100,000 years to a million years worth of climate history. Drill ships can go deeper, and here's a picture of our recent coring expedition. I have to show this because my wife, my newlywed, we're actually newlyweds, but so my new wife actually thinks this is the ugliest shirt ever created, and the only time I can wear it is when I'm away on oceanographic cruises. So this should be very embarrassing to her that I'm actually showing it here today. But anyway, this gives you a sense of the operations of taking a sediment core on ship. This barrel of roughly 10 meters gives us what I'd be sort of holding sediment at the bottom of that core that was deposited roughly 100,000 years or so ago. Then this is a slide that I took from Wolfberger, actually. In much the same way that we look at the chemistry of coral skeletons, when you disaggregate the sediment core, what you find are billions and billions of the remains of microscopic organisms, zooplankton in this case, foraminifera, that live not only in the surface of the ocean, free swimming, but also that live right at the seafloor, the so-called benthic organisms. And by looking at the chemistry of these remains of the fossil zooplankton or fossil benthic organisms, we can actually get a record and have captured and reconstruct a record of what's happening not only in the surface of the ocean through time, but also in the interior of the ocean through time. So this is a way that we can get at the overall overturning or the internal machinations of the ocean on timescales of thousands of years. So one of the most useful tracers that we can use in deep sea sediments is actually dating these microscopic, the remains of microscopic organisms in deep sea sediments. The reason why it's useful is because the ocean is actually tagged with different chemical characteristics, and these organisms actually, when they grow in the seawater, pick up those different characteristics of the water masses. So what's shown here is the radiocarbon or carbon-14 content of the seawater. So if you were to date water in the Atlantic Ocean, you'd get an age of roughly 500 years, but if you went to similar depths in the ocean in the Pacific, that water would give you an age of over 2,000 years. So we can use this as a tag, just like a dye tracer in a sense, to tell us not only how fast the ocean is working, but also the various influences in places of the different water masses coming from the Atlantic versus the Antarctic Ocean versus the Pacific Ocean. So that just gives you a very brief flavor of what it is that we actually try to do in looking at deep ocean sediments. I'll just finish up by illustrating what we did last year, which was to take sediment cores off the coast of West Africa, where this is a bathymetric profile. The continental shelf is shallow, going down to the deep ocean at greater than 4,000 meters. And so at every location here, the seafloor actually intersects a different water depth, obviously, and therefore the benthic organisms growing there capture a different water mass and water characteristic. And so we can sample the interior of the ocean that way. Oh, this didn't come out so well. Here's a cross-section illustrating that very concept. This is the image going through the seafloor, and image of the actual water characteristics. This is sediment, this is the water, and the point is that as we march down the continental slope, the seafloor intersects water that sank in the Antarctic, then that overlies water that sank in the North Atlantic. So we ought to be able to eventually figure out the interplay of these different water masses and how the overturning circulation might have changed in the past. Now, just cutting to the quick, since I don't have time to get into detail the results along these lines, what I can say by way of summary is that so far we really don't have any sufficient data to say what the ocean was doing over the course of these cataclysmic climate changes recorded in Greenland, the stuff of the schlocky movie. So far we can't actually discriminate between the various causes, possible causes for that instability that clearly did occur. So as a consequence, really we can't offer any intelligent comment about the likelihood of future instability in this system in a global warming scenario. Some people claim that it might be possible that we would kick this conveyor, overturning circulation, into another mode of operation that would change climate dramatically. But basically, all we know that is that it did happen in the past. But since we don't know why it happened, we can't make any projection into the future. On the other hand, to end on a more positive note, what we can say is that we're making very strong progress in filling out the picture of observations from the Ice Age ocean. And so we're just starting to be able to chart the interior of the ocean in a way that will allow us to tell us why it changed so abruptly during the last ice age. And once that happens, we should be able to narrow the uncertainties in projecting the future considerably. I think it's safe to say that the Earth won't go into extremes like this tomorrow, or for that matter, any point over the next couple centuries. But certainly, you can't discount the possibility that very strong climate changes might occur simply because we know and have very clear evidence that they did occur. Okay, thanks very much.